The Darling National Demonstration Wind Farm and South African White Paper on Renewable Energy. He is now the project manager for the WindDep GEF project titled South Africa Wind Energy Program, SAWEP, which he started from 2008 to 2010. And this is taking as a phase 1 and has worked as Sanidi on the Wind Atlas for South Africa, WASA project, and currently is the project manager for the SAWEP phase 2. So we'll be presenting Mr. Andre Otter's presentation.
Morning, Program Director, ladies and gentlemen. I will be introducing the UB mini-grid wind integration feasibility study. I will touch on 2 topics, the South Africa Wind Energy Program in general, and specifically component 3, the UB mini-grid project. South Africa Wind Energy Program is a multi-year technical assistance project funded by the Global Environment Facility with the Department of Mineral Resources and Energy as the SAWEP executive country office with project management support by the South African National Energy Development Institute. SAWEP supports the government South Africa promoting the large-scale commercialization of wind energy. It consists of a project coordination unit comprising of the SAWEP project manager and DMER project manager that are responsible for implementation of the SAWEP project document, coordination, and also provides secretariat functions to the SAWEP project steering committee comprising of the DMERE chair with key national government departments as members, DSI, DTIC, Higher Education, Environment, Forestry, Fisheries, UNDP, and SANEDI. SAWEP has been rolled out in a phased approach. SAWEP Phase 1, 2007 to 2010. Highlights of that phase were the Green Power Guarantee Fund that supported City of Cape Town 20-year power purchase agreement with the Darling Wind Power Company, which is basically South Africa's first wind IPP, support of the Wind Atlas for South Africa Phase 1, and also supported establishment of the South Africa Wind Energy Association. SAWEP Phase 2, the current phase 2016 to 2021, comprised of 4 components: monitoring and evaluation of the implementation of local content requirements, very much focused on the reprogram optimization thereof, resource mapping and wind corridor development support for policymakers, basically a continuation of WASA. We did WASA 1, WASA 2, currently busy with WASA 3, and continued support to the government in terms of wind energy policy and the wind industry. Support for the development of small-scale wind sector, which is the topic of the day. We'll go more into that. And then training and human capital development for the wind energy sector, specifically focus here on supporting institutions and students regarding wind energy training. Example here, supporting wind turbine service technicians at students at Saratec. Going specifically on component 3, support for the development of the small-scale wind sector. When we started the implementation of SAWEP in 2016, we undertook a review of the small-scale wind sector in South Africa with benchmarking with international developments. Key findings and recommendations from that review study: already a small and local and export market. In fact, small-scale wind is the renewable technology that first entered the export market years back and actually still exporting today. When you compare small-scale wind with PV, it's not so glamorous, it's not so visual. So there is a challenge to create more awareness around small-scale wind. That would also stimulate the market for small-scale wind. And SAWEP project to address that is indicating to support a small-scale wind pilot project, but we quickly realized that's not really going to help us. We really have to focus on key applications, integration of small-scale wind, which should be able to create a critical awareness on the potential of small-scale wind and thereby assisting the market growth. Thereby, SAWEP is then focusing on supporting small-scale wind in terms of integration with mini-grid systems and also small-scale wind in terms of water pumping at government entities like schools and clinics. Here, not so specifically focused on the water supply. There's already several small-scale wind water pumping systems supporting schools and clinics, but specifically looking at a holistic approach where the integration of that with the school curriculum, with the school systems and projects, food gardens, and so on. And then finally, water supply in rural off-grid areas still the largest market in South Africa for small-scale wind. And we hope through this program that market will be further stimulated. Specifically coming now to the UB mini-grid wind project. After we did a review study, we were then looking for opportunities to collaborate or link up with for the piloting of small-scale wind, specifically in a mini-grid hybrid configuration, and obviously also with the schools. At that stage, the Eastern Cape provincial government were busy with Saxony Lower State in Germany, developing the Upper Blinkwater mini-grid project at nearby Fort Hare. They were using as one of their inputs diesel generator, and they were then also very much interested to expand the renewable resource input. At that stage it was only solar. They were interested to integrate with wind, and we were looking for the opportunity to integrate with the hybrid system. That was then a good match, and that started the collaboration with the UB mini-grid, where we very much focus on supporting the wind component. We're making use of the CSIR Energy Centre that has been capacitated through the WASA project, specifically on the wind resource assessment, and also their expertise regarding energy systems, modeling, and applications. Specifically, the UB mini-grid wind component has two objectives: looking at local-to-local transfer to the affected Eastern Cape communities, Fort Hare University, nearby Fort Hare University, and specifically looking there at the skills and wind skills and resource assessment of CSIR by integrating, utilizing Fort Hare students. This is also co-funded by the CSIR, and then looking at the technical support in terms of the wind resource assessment, the design and the specific parameters for the appropriate small-scale wind turbines to be introduced at Upper Blinkwater, and then also looking at the whole thing about reliability, sustainability, the cost and financial aspects. Ultimately, the goal of the UB mini-grid wind component is optimized integration and usage of small-scale wind turbine with mini-grids for replication and support of the small-scale wind turbine market growth in South Africa. This is basically a schematic of the UB mini-grid showing its main partners, or what you can call it the founding partners, Eastern Cape Provincial Government, with the Saxony Lower State Germany, the Raben-Maslaba local municipality, and then obviously also the UB Blinkwater community. The current mini-grid comprising of the PV generator of about 75 kilowatt, diesel generator 44 kilowatt, PV and battery systems, and then also storage. And that's already in operation since about June last year, and we are now in the process of integrating the wind component. Going a little bit deeper in the scope of work for the UB mini-grid wind component, local knowledge transfer, specifically here looking at sourcing and pointing, utilizing postgraduate students for assisting with the wind resource assessment, with the wind integration systems, and also with the social appraisal methods in the community. That's all been done. And then the knowledge transfer to Fort Hare and other interested tertiary institutions and individuals by means of a short course, what we are doing today. Then community introductions to wind component via the government, the Eastern Cape Provincial Government appointed social facilitator. That was done. Technical support, looking at assisting the local wind resource using measurements and numeric modeling techniques. That was done. Also utilizing the LiDAR in that process to expedite the wind resource assessment. The sourcing, sizing, and place of local small-scale wind turbine technologies, that was done. We signed a contract end of last year with Kestrel for the supply installation of 6 by 3.5 kilowatt small-scale wind turbine systems, hopefully in the next 2 months to 2.5 months. Simulating the impact of these small wind turbines and existing solar diesel battery mini-grid for optimizing the complete unit. Assessing and monitoring the financial and operational aspects. Obviously, we would like to replicate a cost, financial efficient system, and then supporting the owner's engineer tender specifications evaluation. And then very important, identify the monitoring evaluation hardware and software, and then defining the measurement parameters in terms of technical, social, environment for the wind component, which will then be implemented in phase 2. That will also be done through the CSIR with Fort Hare. Phase 2 will then also look at the 1-year defects period of the turbines implemented, operation and maintenance thereof, capacity building, and then the monitoring evaluation implementation. And then in a longer term, looking at the income generation and sustainability. And in that, in short, is an overview of the wind component and its components, scope of work, which you will then hear today much more detail, specifically on experience, the technical aspects, the social aspects of that. And I wish you a fruitful workshop, and thank you.
Thank you for that. Thank you, Lindo, for assisting with the presentation. Sorry for the technical difficulties on our end. We are a bit behind time, so I'm going to introduce the next speaker, which is Dr. Kitesa Roro. As a background, Dr. Kitesa is a physicist with over 12 years of experience in renewable energy research, development, and innovation. Dr. Kitesa Roro received his PhD in 2009 from the Nelson Mandela Metropolitan University and subsequently spent several years working as a postdoctoral researcher, first for the University of Pretoria and then later in the CSIR National Laser Centre. He is presently a principal researcher and a research group leader for the Energy Supply and Demand Research Group within the Energy Centre at the Smart Places cluster of the CSIR. The ESD research group underpins the Energy Centre work in solar, wind, renewable energy production, supply focusing, energy efficiency, demand response, and thermal energy optimization, inclusive of thermal energy efficiency, recovery, and storage. The techno-economic viability of emerging and existing approaches to energy supply and end-use efficiency are independently assessed to provide impartial advocacy to industry and consumers. He is also involved in a number of initiatives of the Energy Centre, including establishment of an outdoor PV testing facility, defining the research agent of the solar research, support to the South African government on solar energy research, development and innovation roadmap, development as well as supporting the growing PV industry in South Africa. He has authored about 30 research papers, delivered presentations in various local and international conferences, and runs several international collaboration, and is presently supervisor of 5 postgraduate degrees. So with that, I'm going to give our technical team to present Dr. Kitesa's presentation. Thank you.
Thank you so much, Program Director, for the introduction. I would like to set the scene by introducing about the CSIR and CSIR Energy Centre, as well as the wind energy. The content of my talk is as follows. I will start with a brief introduction of the CSIR, give an overview of the Energy Centre and some of our research activities, and I will conclude by providing a background about the UB mini-grid project, which is the wind integration portion. The Council for Scientific and Industrial Research, the CSIR, has got a mandate, which is to conduct directed and particularly multidisciplinary research and technological innovation to foster in the national interest in the fields in which, in our opinion, should receive preferences, industrial and scientific development, either by ourselves or in cooperation through principles from private and public sectors to contribute for the improvement of the quality of life of the people of the Republic. Recently, the organization has undergone a new strategy definition, and our new vision is as follows. We are accelerators of socio-economic prosperity in South Africa through leading innovation. How we do that, we collaboratively innovating and localizing technologies while providing knowledge solutions for the inclusive and sustainable advancement of industry and society. How we do that in our value is epic excellence, people-centered, in integrity, collaboration. We excel at research and development and industrial innovation solutions that address South Africa's challenges. We care about our people. We value integrity in ourselves and in others. We are keen to learn from one another and collaborate across the organization and with external partners to ensure our work has best chance to innovate a better future for South Africans, where the UB Mini Grid project provided such a platform for us. The organization have got 5 strategic objectives. The first one is to conduct research, development, and innovation of transformative technologies and accelerate the diffusion. The second one is to collaboratively improve the competitiveness of high-impact industries to support South Africa's re-industrialization. The third one is to drive socio-economic transformations through RDI that support the development of a capable state. We do that through building and transforming our human capital and infrastructure. And we, like any financially sustainable institution, we aspire to diversify our income to maintain our sustainability and good governance. The research units within the organization have been clustered into 9 clusters based on the outcome of the recent strategy definition. And we do research from advanced agriculture and food, chemicals, next generation health, future production manufacturing, mining, defense and security, smart places, smart mobility, next generation enterprises and institutions. So the Energy Centre is clustered in smart places cluster, which is in the bottom left corner of the presentation. The CSIR Energy Centre research groups were formed based on the energy value chain. We've got research groups which focus on technology, which focus on systems, as well as end user. We do research from energy supply and demand, electrochemical energy technologies, mainly batteries, fuel cell and supercapacitors for storage, energy systems, energy modeling, energy system design, energy system operation, and the end user one, which is energy industry, industrialization support, socioeconomic analysis, techno-economics, SMME development, and the recent very hot topic, which is just energy transition. So we walk the walk. We've got a living energy lab platform where we demonstrated in our campus we're using it as real world implementation of our research program. Recently, we have installed 2 megawatt of PV in our campus. We also, within the program, we also have a program looking through testing, development, prototyping, and field deployment of energy storage solutions. We partner with a number of institutions, such as in the energy domain, of course, from Department of Mineral Resource and Energy, Science and Innovation, ESCOM, IDC, Green Cape, HISA,
NISA, in our institutions such as our academic institutions such as University of Pretoria, Nelson Mandela University, University of Cape Town, Northwest University, University of Wits, and we also collaborate with international organizations in Germany, Australia, US, and many other African and other countries. Our recently crafted RDI plan has got about 8 to 9 core focus areas, from energy supply, network and operation, energy use, storage, innovation, just transition and industry support, sustainable energy future, smart utilities program, and it's highly industry facing, need driven. The energy supply and demand research focus area focuses in 4 areas. The first one is solar energy, the second one is wind energy and supply forecasting, the third one is thermal energy, the fourth one is energy demand. Just to give you a snapshot of some of the flagship projects within the group. The first one is a project which focuses on mapping the South African wind energy resource and benchmark that with global wind atlas, is the WASA project, which aims to improving the wind atlas of South Africa. We does that in a collaboration with SANEDI and other project partners. And we have been spearheading 2 work packages. The program has got 4 work packages, and we've been spearheading that from 2010. And the CSIR is responsible for all meteorological measurement campaign, data management and quality control, micro-scale modeling, and mast operations, which involve about 19 standardized instrumented masts that are spread across 5 provinces. And now we are about to conclude the phase 3, and I'm hopeful that the WASA 4 will continue in foreseeable future. The other flagship project within our research group is focusing on the establishment of a world-class research and testing facility for solar PV modules and systems reliability, which aims to improve the cost competitiveness of solar PV system for greater deployment of the technology. So this is mainly CSIR self-funded, but technology localization implementation unit of Department of Science and Innovation partnered with us. The project aims to establish a solar PV research and testing facility just to enhance our ability to support the deployment of PV technologies and as well as PV system design and optimization in South Africa and globally. Of course, the outputs of the work will increase the understanding of the performance of PV in South African climatic condition. This facility comprises indoor and outdoor test facility, which is unique in African continent, and in ability to do the extended reliability testing beyond the qualification testing the industry performs. And the facility also aspires to become a reference laboratory in Southern Africa for PV module and system performance testing with the establishment of recognized testing and evaluation procedures. The research group has got the wind team expert know-how for wind measurements, from measurement campaign design using standalone wind mast or remote sensing wind measurement using a LiDAR, even in remote and complex terrain. We've got know-how in installation and commissioning, supplying wind mast and manage their certification, and we are able to support sourcing and specifying instrumentation. We've got know-how in data quality and assurance, as well as operation and maintenance of the wind measurement campaign. We can perform meteorological orientation maintenance, and we can work with affiliated original equipment and manufacturers. We also has wind team has got expert in resource mapping, thanks to the WASA project. We have got expert support. We can give expert support from concept development, feasibility study, site data, mining feasibility check using numerical data, and the measurement using MAST or LiDAR, and resource modeling using industry standard software. And we can also support in wind turbine or wind farm feasibility studies by performing pre-feasibility calculations and provide preliminary levelized cost of electricity estimates. Our solar PV team has got experts for the execution of wind project across the project life cycle, from concept development in feasibility studies, resource assessment, gone or gone decision, support with environmental impact assessment in partnership with a sister research group within the cluster. And we can also support the PV system engineering from energy yield optimization, techno-economic optimization. We can also do PV power plant development support in PV power plant development, PV power plant project execution, PV plant monitoring and servicing. Just to put things in context, I would like to give you the international and South African wind energy market, just to give you some statistics, just to excite. In 2020, 232 gigawatt of new wind and solar PV capacity has been installed globally. Out of that, 139 were PV and about 93 were wind. This tells you that wind is really playing a significant role in deployment of new energy technologies globally. Thanks to the effort with WASA program, the true potential of South Africa's wind is becoming clearer. This is really, it always excites me when I see the development and the impact the WASA program is making. You know, I mean, in 1995, late 90s, between 1995 and now, there's significant difference in the quality and of the resource and understanding in our understanding of the country's resource. Thanks to the WASA project, this is really demonstrate how the project has been impactful. Indeed, South Africa has got world-class onshore wind resource. South Africa also has a world-class offshore resource. Recent World Bank Group study on offshore wind technical potential for South Africa quantified. South Africa has got about 645 gigawatt of offshore wind capacity, and that really suggests a very good opportunity for further strategic research. Just to give you some statistics, the fixed technology is about 60 gigawatt, whereas the floating is like about 10 times more than the fixed, which is about 600 gigawatts. This definitely warrants further investigation to quantify the opportunities in this area. Hence, the future wind resource assessment effort, I'm sure, should also include the quantification of the offshore wind resource. The 2019 IRP, which has been gazetted, clearly show that wind is going to play an increasing role in the South African energy mix. And yeah, definitely wind is going to play a significant role. As per the plan, starting from 2022, there's about 1.6 gigawatt of PV that will be added every year. Just to give you some statistics for the previous Renewable Energy Independent Power Producers Procurement Program, there's a significant, dramatic cost reduction. I'm sure the new bid window that will be commenced cost reduction. PV system price in the country reduced, utility scale PV system price reduced by 83%, whereas wind reduced by 60%. This clearly demonstrates the cost of wind and PV are significantly coming down. From the 1st of November 2013, where we began with the program, up until last December, about 2.5 gigawatt of wind has been added, about 2 megawatt of large-scale PV, and half gigawatt of CSP become operational in South Africa. And in terms of energy production in 2020, 12.4 terawatt of wind, solar PV, and CSP were produced in South Africa. Out of that, 6.6, just over half of that came from wind. And in terms of annual capacity factor, last year the wind shown about 35% capacity factor. In 2020, coal dominated the energy mix at 184 terawatt of the 219 terawatt of total system load, whereas PV, wind, and CSP about 12.4. Interesting statistics, as you can see, the wind contributed about 3%. As it goes by, the contribution of wind is really becoming very, very increasing and hence important. Another interesting outlook in terms of the cost reduction, reputable organizations such as NREL, Bloomberg, CSIR, and Danish Energy Agency all predicted. They follow the same trend, and it looks like in the coming years, the cost of the technology is going to decline continuously, and this really suggests that wind and per se renewable energy is going to play a significant role. Just to give you a quick background, I'm sure Andre has done a very good work. The mini-grid pilot project was initiated to electrify the small village in Upper Blink in Eastern Cape Province, led through collaborative effort between the Eastern Cape Province and Lower Saxon state of Germany. It is aimed to be a test case for providing high-quality energy to a deep rural village that's not connected to the national grid. It's a hybrid approach, and we are very grateful that we have been bestowed to spearhead the wind component feasibility studies. The study preceded by conducting a survey to quantify the demand requirements, and according to that study, each household will consume approximately 1,400 kilowatt hour per year. Annual demand would be 93,800 kilowatt per year, and the estimated annual energy output is 30 megawatt, and the addition of wind into the existing mini grid will definitely is assumed to displace the diesel. The study has got 4 4 phases. One can easily divide them in high-level 4 phases. The first one is high-level resource assessment phase, where we deploy our LiDAR for on-site measurements, and we use the industry standard WASP modeling. Using the WASA data, we generate wind climate models for proposed wind turbine generators and identified the appropriate small wind turbine generator, and we estimated the annual energy production. Hence, we concluded with the feasibility of comparison of several different options. And we also provided in the study detailed designing. We supported in the tendering phase, and now we are busy supporting with the implementation phase. My colleagues will give a detailed presentation for each phases, and others that we undertook the past year or so as part of the wind integration component. Thank you so much for listening, and I will answer any questions that you might have. Thank you.
Thank you, Dr. Roro. Thank you, Lindo, for sharing the presentation. I think going on forward, we will run much more smoother given the new arrangement. So I'm just going to go to the next presenter, introduce the next presenter. Please also don't forget to ask any questions on the chat room, and Lindo will keep track of them. So the next presenter is Mr. Jody Julius. He'll be presenting on wind resource assessment. Jody is a graduate in training junior engineer who has a bachelor's degree in mechatronics engineering obtained at Stellenbosch. He currently works for the CSIR, where he manages data obtained from wind instruments, LiDAR or wind mast, and manages and assists in construction and deployment of a 10-meter wind mast. He's participated and assisted in social community interaction and knowledge transfer to ensure social awareness. He's also participated in stakeholder, external or internal interactions and performed modeling in WhatsApp. He's programmed scripts to assist with data management and assist in producing reports for clients and interested parties to depict potential of the wind resource feasibility study, document installation and social interaction work conducted, as well as proposal. He also manages the setup and operation of LiDARs and assists in environmental impact assessments. So Lindo will share the presentation for Jody.
Good morning. My name is Jody Julius. I'll be doing a short presentation on resources. This presentation will give a broad outline of a typical wind resource assessment and will highlight the work at Upper Blinkwater resources. So a brief background, the project was to create a mini grid for a small community within the Eastern Cape. The community has approximately 70 households that has no access to electricity grid now or in the foreseeable future. This project is also set to provide economic opportunities for the locals and improve their living conditions. The system comprised of a PV system, battery storage, backup diesel generator, and a wind turbine system. And it's also set to form a blueprint for similar projects within the future. So just a quick step through of what the resource assessment entails. So first you need to define a level of assessment. So if it's only the pre-feasibility and it's not set to the development of a system is not set yet, so then it's okay to use model data if you know that the development is set to take place. You require a full resource assessment, and this requires on-site measurement campaign. Second step, the step after, once you do level of analysis, you can go through the site selection process. In this project, we use the power density maps to make the selection process. Once you've found a location for siting, you conduct a measurement campaign with one of the measurement instruments. Now with a full data set, you can actually model a proposed development. And then with this, you can conduct a feasibility. Using the feasibility matrix, you can actually select the most suitable development. So for this project, it was already outlined that we'll be conducting a measurement campaign, but it was limited to 6 months. So that kind of made our selection of the instrument, it limited our selection of the instrument. So constructing the met mass, the time frame didn't allow it, but we still looked at the various options. So met mass uses cup anemometers to take measurements at the point where LiDAR is positioned and is very mobile, can be put on site within a week. You can have it there taking measurements at different heights, whatever your preferred measurement height is. So with this campaign, which is much shorter, we did get to position our Zephyr on site for 6 months. So we did utilize, for site selection process, we utilized the power density maps that was created through the WASA project, the WASA initiative, started in 2009. This map was created in 2018, so the resources used was, you can say from the year 2009 to 2018, as the map was created in 2018. If I'm not mistaken, there is a more up-to-date map for 2020. Taking a more zone-in approach, you can clearly see that where we positioned our wind met mass on the ridge, there was a much higher power density and therefore potential producing power. And then where we positioned our LiDAR, which was closer to the community, it had a much lower potential power production. So we have our two predetermined sites, but the reason we had our main measurement campaign close to the community, because we found that although site 2, where we positioned our met mass for 1 month, had a higher potential for power production, there was added cable losses, and therefore site 1 was more favorable. So we positioned the LiDAR at site 1 for 6 months and 10 met mass at site 2 for 1 month. So this measurement campaign was conducted, and then with the data procured through the measurement campaign, we looked to model a proposed development within WASP, which is a commercial tool, software tool. Like many other, you get something called WindPro as well, which also allows you to model proposed wind farms. First, we start by developing the observed wind climate. So we have the set of data. So with the data, we actually need to create observed wind climate. So to create this observed wind climate, we first require a full years of data. So unfortunately for the UV mini grid, due to time constraint, we could only conduct a 6-month measurement campaign, but we did expand the data to a full year of data to ensure that seasonality sensitivity is limited. We use the MCP method, and therefore it covered a 4 years of data. So the basic steps I would follow through when creating observed wind climate. So I open the wind climate analyst, and immediately it will ask me to define the location. You can ignore this, but if it is known, it's advised to insert the latitude and longitude as seen on screen. with this now set, it takes you to another page where you can actually define what you can call the file, and then you will right click on your proposed metmask, your observable climate, and then you will click on import dataset. During this, you will just make sure that when it imports that software reads correctly, your parameters are seen at the bottom. So you will just look at, okay, wind speed is wind speed and wind direction is wind direction, the heights are matching up, and the columns are reading correctly. So the numbers is that recording intervals, is that the average time, and just make sure all the parameters are correct. Once this is defined, you can move on to defining the COM thresholds, and then you simply press import. So now the data will be imported, and before creating observable climate, you just need to do some time trimming. So time trimming is done to ensure that you actually do you only select the data you do want to use. So like I mentioned before, it's advisable to use a full years of measurement. So when I say 4 years, I mean say from January, beginning January to end of December, or end of June to, let's say, beginning of June to end of May. So that covering every single month of the year, so that you avoid any seasonality changes. And it might be times where maybe the measurements didn't work out for 1 week, like your data didn't look correct for 1 week. You can actually remove certain sets of data. There's obviously standards that use for that. So if it's a week, I think if it's a week, it's okay to remove. But if it becomes more, you might need to look at shifting, maybe expand your measurement campaign so you actually get a full years of accurate data. And then you will right click on results, and you actually create your observable climate, and you will save this in the folder that you're working with. Your observable climate are created. You can move on to creating the vector map. So they are basic two. The vector map is comprised of two maps, so the elevation map and roughness map. So these are basically the two factors that are considered when you are modeling a proposed development, proposed wind farm. So because the elevation plays a role and the roughness plays a role during the modeling process. So for the roughness, so roughness is an important factor, as you might know, during wind modeling, because the terrain's surface friction has a large impact on the boundary layer flow, and in turn the wind speed at different heights. So when you're modeling course proposed, you have wind measurements at 100 meters, and you might want to actually conduct an assessment at 10 meters or 50 meters, and therefore the roughness plays a role, and even when you move across the terrain. So therefore it's important to have a rough. But you can clearly, you can get a better picture if you perhaps think of water blowing off flat water surface compared to water blowing over a forest or city. So, influence that rain has on, because of the different roughnesses. Plays a big role in how the wind reacts, and the roughness length parameters also is actually defined in meters. So there is a basic category, and there's the roughness or the different roughness classes and lengths, as you can see. So farmland with very few buildings and trees is 0.0 meters, and that's a class of 1. Tall forest, roughness class of 4, 1.5 meters. And so there's different levels, and this roughness map that takes into account the different terrain or different landscape you might be in. So the basic steps are followed to obtain this roughness map. So this is obtained from a web database. So I'll import from a web database. I'll select which web database I will utilize, and then I'll define the location of the map, and once it's defined, I can define the extension of the map, so how far, 10 kilometer by 10 kilometer, depending on the size I want to study, and then I import this map. So a lot of times these maps sometimes do have errors that might occur, so anchoring or joining dead ends, and this can be easily fixed through manually fixed. And do note that these roughness lengths are changeable. So if you were on site and you feel that the roughness seen doesn't accurately represent the study area, then you can change it. The roughness map created, we can move on to the elevation map. So a similar process. So import from a database that you select, and you define the location, you define the extension, you define the height contours, and then you import. And then you can also change these values, this elevation values, depending on if you feel like it's not represented well. So now finally, with the roughness and elevation map created, we need to combine these two to create the vector map, and then you should save it as a .map file. And this is actually the map that's used during modeling in WASP. So now I'll just run through the basic process of modeling in WASP. So it's just creating the workspace that will enable you to get the results like the annual energy production, the power density of the area, and best position in the turbine. So it's just like a very basic process. So first you open WASP, and there's a window that will be shown. So once it's open and you click on File and then New Workspace. So the first thing I do is add the vector map that was earlier created, which is the roughness and elevation map. So it's just a representation of the terrain of the area. So the modeling software knows how to react according to where you are conducting an analysis. And this is simply done by right-clicking on your workspace and then selecting Insert File and then selecting Vector Map. So now with the vector map added, we would like to add a generalized wind climate. So to create this generalized wind climate, you actually need to first go to your workspace and then insert new generalized wind climate. So with this generalized wind climate added, you can provide in the generalized wind climate, they'll ask you to provide the X and Y coordinates of the met mass, and this is done by simply indicating the UTM coordinates of the X coordinate and the Y coordinate. So you need to convert that from the machine you use latitude and longitude coordinates. And then once these are defined, it will require you to input the observed wind climate we earlier created from the data set we obtained from our measurement campaign. So with this created, now you have a workspace as seen on screen. You will have your generalized wind climate selected on screen, and at a lower project level, you see that it's you have your met mass and you also have your observed wind climate. So as you can see, there is a warning sign. So what you do is you right click on the generalized wind climate and you select generalized wind climate, and this will take you to the page that's shown on screen now. And you can see the mean temperature, the altitude, the pressure. Those parameters aren't defined yet. So the WASP modeling tool does have an automated system, so you can simply just click Get, and it will utilize the position of the site area and then get that information to satellite data. With the generalized wind climate now created for the area, you need to create your proposed development. So I start by inserting, so I right click on the workspace and insert new, and then I'll insert my wind farm, and I will define. So I'll define my wind farm by naming it. So in this case, I named it community wind farm. So then what's a community wind farm? Now I can right click on there, and then I'll insert from file, and then insert the turbine generator model that I'll be using for this development. Now with the turbine generator model defined, so the workshop modeling tool knows exactly the parameters utilized when modeling and how the wind turbine will produce during the generation of the power. So as the wind blows, the turbine moves, and these parameters are now defined through that earlier inserted wind turbine generator file. We now need to define our sites, our wind turbine site. So where we would like to position these wind turbines. So this is done by right clicking from into wind farm. This within the WASP project file workspace, and then I'll select insert new, and then I'll select turbine site, and this can be repeated. This process is repeated when you want, depending on how many turbines you actually want to insert in this wind farm. And this will require you to once again insert the X and Y coordinates for the proposed wind farm, wind turbine, and then also indicate the hub height of this inserted wind turbine. So with the wind farm now positioned, let me say the wind turbine's position and the wind farm now configured, I will insert a resource grid. This is done by right clicking on the workspace, insert new one, and clicking on resource grid. Here I will enter the height at which I want the calculations to be done for the resource grid. So this is usually done at the hub height of the selected turbine, and then so now with this defined, I will right click on resource grid and then select show resource grid. So I can define in this spatial view the area I want to assess. So it's done. So in there, I'll go to spatial view and click on the edit button. So here I can now indicate what area I want to assess. So like the resolution, the columns, the rows. So at what resolution I actually want to formulate the power density. So for higher resolution and larger area, this analysis or modeling will take much longer. So you consider these factors when selecting the resolution. So now with the resource grid defined, I can actually now plot or obtain the power density map, the mean wind speed, and these are all valuable information towards the resource grid now defined at the hub height of the turbine. You can clearly see that yes, the turbines are actually positioned within the valley at Upper Blinkwater, which is actually at a much lower wind speed area. Power density is much lower in that area, and in fact the ridge is much higher. But as mentioned before, although the wind speed is higher on the ridge, the power losses experienced through the cables outweighs this, and it's not as beneficial, or the wind doesn't, the power production potential isn't as beneficial to motivate the movement of the wind turbines onto the ridge. So, but we do still assess for on the ridge because we have measurements on ridge and we have measurement in valley. So we will utilize the matrix in a later stage. to assess which is the better option. So now we have a resource grid that tells us the different areas, wind speeds across the whole site area, the wind speeds, power density, the annual energy production per different areas. So, and we have a proposed wind farm, so we can move around the turbines, and we can actually define how much this wind farm will produce over a year, and we have a full set of results to make an informed decision on the development. So as mentioned before, so with the simulated model of the wind farm completed, we can obtain the following as mentioned before. So we can obtain the wind speed parameter, wind direction parameters, location energy density mapping, so that enables the developer to position the wind farms to configure the wind farms optimally, and we can obtain the expected wind farm annual energy production, and we can go down to actually assessing each specific wind turbine's annual energy production. And this obviously enables the modeler to optimize the placement of these wind turbines. So now that was the basic approach followed during my resource assessment. So with the resource assessment, so with the modeling completed and all the results at hand, we developed a feasibility matrix, and this will enable us to do an unbiased selection process. So we know that 2 different locations were assessed, so the location on the ridge and location closer to the grid, developed grid for the community, and closer to the power station. And then we also know that we are assessing 3 different turbine configuration types, and this provides 6 possible solutions that we would be assessing further. And from this pre-feasibility matrix that assesses the AEP, the capex costs, the LCOEs, maintenance, and rated each solution according to these factors. We actually found that the Kestrel turbine at location 1, which is close to the grid, close to the power station, and where the LiDAR was positioned, was actually the preferred solution, and ended up choosing the Kestrel at this location for further development. Thank you.
Thank you. Right now, we are meant to take a break. Initially, the break was meant to be 10 minutes, but for the interest of time, I would suggest that we perhaps take a 5-minute break instead, and then come back within that 5 minutes, the rest of the 5 minutes. So I don't know if anyone objects to that, but yeah, that's my suggestion for now. So that means from 10:30, you will be coming back at 25 to 11. So at 10:35. So does anyone object to that? Or is that all right? Okay. Okay, so I will call in everyone at 10:35, and then we'll continue with the next presenter. So the next session is looking at potential assessment of wind energy in the UB community, and this will be presented by Ngwarai Shambira, and he will be joined by Prof. Makaka. In terms of Ngwarai Shambira, he is a PhD physics student with a research focus in renewable energy technologies, focused on wind energy at the University of Fort Hare, South Africa. and his current research interests are in the technical, socio-economic, and environmental aspects in off-grid and standalone application, as well as on increasing the power output of wind turbines in low wind speed areas through augmentation processes using concentrators and diffusers. So I'll give to Lindo to share the presentation for Ungwarai.
Mr. Shambira will give a presentation on potential assessment will give an insight of the wind density and establish wind power density of Upper Blinkwater community. That is informing on the criteria of choosing the right wind turbines. Mr. Shambira will also elaborate the techniques he used in implementing the right turbine sizes. And Mr. Shambira is a PhD student in his third year, and he will give us a very clear narrative of his report on the assessment of wind energy potential in the Upper Blinkwater. Mr. Shambira, please take over.
Thank you very much, Professor Makaka. My topic, as alluded, is potential assessment of wind energy in the Upper Blinkwater community. Outline of my presentation. I'm going to start with a brief introduction, why the evaluation of wind potential, methodology, results, discussions, and recommendations. Conclusion will also follow, as well as lastly, I'll look at challenges, next stage of the project. Even though South Africa has made greater strides in utilizing wind power, just few scientific researches have been presented on wind potential assessment, and Upper Blinkwater has not been spared as well. But from researches done on wind resource in South Africa, found noted that wind resource was more secure and available in winter, that is June, July, and August, than in the summer season, that is January, February, and March, and was also reliable during the day than at night. Manyereze and Prof. Makaka also found that Fort Beaufort area has got a maximum wind power density of 123.1 watt per square meter at a height of 15 meters above the ground. At 6 sites, which included Fort Beaufort area, again, Shoniwa and Prof. Makaka also revealed that the wind power density for the sites ranged from 34.7 watt per square meter at Fort Beaufort area to 207.8 watt per square meter at Port Elizabeth. Evaluation of wind potential is important because it will establish wind power density of the Upper Blinkwater area. It will also establish the feasibility of the wind projects on this site and reduce investment risk. It will maximize its wind power generation efficiency by choosing appropriate wind turbines that are suitable for the prevailing wind speeds. Methodology. The wind data was collected at 10-minute intervals using the LIDAR at heights of 1,100 meters above the ground level from April to November 2019, which is approximately 8 months. But in our analysis, we only used wind data at 11, 20, and 30-meter heights. Statistical analysis of wind speed data was done using the 2-parameter Weibull probability distribution function given below. This function determines the number of occurrences of specific wind speeds at a site, where C and K in this function determines the form of Weibull distribution K. The C represents the Weibull scale parameter, and its units are meters per second. The values of C indicates the distribution curve and the range. So they show the amount of wind available at a site. Also, if the values of C are high, the Weibull curve becomes broader. K represents the Weibull shape parameter, and it has got no units. And the value of K indicates the width of the curve. That is the shape of the wind distribution. The values of K between 1 and 2 also shows a shift to low wind speeds. And K values between 2,5 and 3 shows a distribution which is more skewed to high wind speeds. But if K is greater than 3, it corresponds to uniform winds, whilst K close to 1 indicates a highly variable wind speeds. Performance of a Weibull distribution in fitting the observed data depends on the correct choice of the method to calculate our Weibull scale and shape parameters. So in our study, 4 methods were used, namely maximum likelihood method, WASP method, open wind method, and least squares method. The maximum likelihood method is derived from numerical iterations and computes K and C with the formulas shown below, where N in this represent the total data points and VI in the formula represent wind speed for the I time step. And the second method is the WASP method. It is based on 2 conditions. That is, the power density of fitted Weibull distribution is equal to that of the observed distribution. The proportion of values above the average is the same for the fitted Weibull distribution as for the observed distribution. And first, from the formulas given below, K is obtained first using the iterative method. And then we substitute into the formula to get the Weibull scale parameter. The third method, which is the open wind method, it is also based on 2 criteria. That is, the mean power density of fitted Weibull distribution is equal to that of observed distribution. And the second condition is that the mean wind speed of fitted Weibull must be equal to the average of the observed wind speeds. Parameter. Lastly, the least square method is we are going to use it to obtain C and K parameters through the use of a cumulative distribution function by transforming to this equation, which is a linear equation, by applying logarithm transformation 2 times. In this equation, M, which is our gradient, represents the shape parameter, whilst the y-intercept is the one that we use through substitution of K to obtain our Weibull scale parameter by this equation. Statistical methods used to fit the wind data plays important role in making decisions about the wind potential of a site. Hence, they need to evaluate their effectiveness. Otherwise, overestimation or underestimation of power available will result in. So 7 statistical indicators were used for the goodness of fit tests. The first indicator is the mean absolute bias error. Second, the root mean square error. And these 2, for them to show effectiveness of the methods, their values must be close to 0. Whilst correlation coefficient, coefficient of determination, and index of agreement, they must be close to 1. And if they are close to 1, it shows that there is a strong relationship between our Weibo distribution calculated from our methods and the observed data. These are the results.
You don't know what the side of the shovel. You don't have to tap anything like that.
Wind data, statistical wind data at the Upper Blinkwater area. And from the table, at all the heights, the overall average wind speeds were between 4,36 and 4,78 meters per second, while standard deviation was between 3,04 and 3,38 meters per second. The standard deviation values in all the months showed an increasing trend with height. However, this variation is significantly small when compared to the variation in the average wind speeds. The skewness for all the months was positive, as shown in the table. This implies that values of measured wind speed data are above average wind speed and therefore depicted a better wind performance. The skewness also depicted a noticeable decreasing trend as the height increases. This could be due to more stable winds experienced at greater heights. Same pattern is observed for ketosis, as it also decreases as the height is increased. The values of ketosis for all the months were below 3, which indicate that the wind speed data has a few extreme values. But in July and November, ketosis values are negative for all the heights, which indicate lighter tails and a flatter distribution. The graph shown here, it shows the daily average values of wind speed of Upper Blinkwater area. During the morning, before 8 a.m., a stable wind is experienced. The wind speed then increases steeply to a maximum values of 5,9 at 11 meters height, 6,2 at 20 meter height, 6,4 meters per second at 30 meter height above the ground level. This happens between 12 o'clock and 1 o'clock. During the afternoon, the wind speed profile is dome-shaped, as shown in the graph. In the evening, between 9 o'clock and 10 o'clock, lowest values of daily average wind speeds are recorded. 3,3 meters per second for 11 meters height, 3,5 meters per second for 20 meter height, and 3,8 meters per second.
Lindo, your mic is muted. Not too sure what happened there.
The graph shows the mid-monthly Weibo scale.
Okay. Are you playing?
Yes, I am playing. Is the audio not coming through?
No, it's not coming through.
Okay, apologies about that. Let me just try and reshare.
Weibo scale and shape values. This generally shows that there is more potential of wind energy at 30 meters height, especially in the month of June and July. The K values were between 1,2 and 2,4, and this generally indicates low winds in the Upper Blinkwater area. The least square method, as shown from the graph here, did not perform well in estimating the values of K. But overall, the K values ranged from 1,389 to 1,727 for all the heights. And the C values were also between 4,667 and 5,308 meters per second at all the heights. Comparison between wind speed frequency distribution function and actual data frequency distribution of Upper Blinkwater are shown through these diagrams, where the blue histograms indicate the actual observed data, and yellow line here, it indicates the maximum likelihood method, and least squares is being represented by a purple line, and the blue line represents the WASP method, and the open wind is represented by the red line here. So the four algorithms at all the three heights portrayed a better fitting of the data with the open wind, WASP method, and maximum likelihood method leading in that order. However, least squares performed poorly when compared to others. The goodness of fit test results showed that the coefficient of determination varied between 0.8680 and 0.9196. So this showed that the two-parameter Weber distribution matched well the actual wind speed data of the Upper Blinkwater. As you can see from the table, the WASP method and the open wind method, they were tightly close in terms of its performance. So a further goodness of fit test was done using 6 statistical indicators to check which one performs the best. So open wind method was ranked first as the most efficient method, whilst WASP method was ranked second, and third maximum likelihood method. The least square method was ranked fourth in terms of performance. So it was recommended that the two-parameter Weber distribution can be used to fit the observed wind data of the Upper Blinkwater area if the Weber scale and the shape parameters are estimated using open wind method. The windrows diagrams shown below provide useful information on the prevailing wind direction and availability of directional wind speed in different wind speed intervals. Based on the wind direction data analysis at all heights, it shows that the dominating wind mostly comes from the northwest direction of the Upper Blinkwater area. Turbulence intensity of the Upper Blinkwater area was also determined. Basically, turbulence intensity simply means the rapid disturbances in the wind speed and direction. And it is calculated using the formula of standard deviation divided by the average wind speed. Its classification was done using the 3rd edition of International Electrotechnical Commission classes A, B, and C. And A is regarded as turbulent. The turbulence intensity is high when you are in class A. So representative turbulence intensity of 0.19 was calculated at all heights. So the obtained value of 19% is above the recommended 16% turbulence intensity at 15 meters per second wind speed, therefore falls in class A. So it was recommended that the site requires wind turbines that can sustain high turbulence intensities, as it reduces the efficiency as well as operating life of wind turbines. Also from the graph, the decrease of turbulence intensity with height is caused by wind speed reaching stability and becoming smoother at greater heights. The results of wind power densities of Upper Blinkwater are also shown in the table given below. From the table, there was a slight difference between the actual power densities and Weibull power densities. This observation endorses a well-known fact that Weibull distribution function is appropriate for fitting wind speed data with precision. So the overall wind power densities estimated using open methods for the Upper Blinkwater was 144.92 at 11-meter height, 171.52 watt per square meter at 20-meter height, and 192.08 watt per square meter at a height of 30 meters above the ground. The site also registered highest monthly average wind power densities between 379 to 498 watt per square meter in July, with the lowest recorded in April. And the April values range from 51 to 70 watt per square meter at 30-meter height. The overall wind power densities were classified as follows. Because they fell in the range of 100 to 300 watt per square meter. And only wind turbines were recommended, with activities such as pumping In conclusion, the assessment is dependent on correct calculation of the scale and parameters, and the four methods used did a good job in that. The Upper Blinkwater is suitable for small-scale wind power generation projects. However, wind data beyond 8 months should be used to authenticate this analysis. So 5 years weather data, which includes Upper Blinkwater area, was obtained from when the solar covering of microgrid during winter is heavily depleted. It is important to assess that a hybrid on standalone off-grid system is the only way to go. Challenges. Due to slow implementation of the wind component, some of our activities on monitoring and evaluation are yet to be carried out. And a scholarly article which compares load profiles collected through interviews and load profiles from measured data is still outstanding. COVID-19 has also negatively impacted on our interaction with my colleagues, especially on producing research articles. Difficult to get. The next stage of the process is monitoring and evaluation. We plan to install micro-meteorological station and the electrical data with the use of data logger for measurements of meteorological parameters. Analysis of high-resolution load profiles data using 4 performance indicators for technically characterizing demand and generation. Developing electricity consumption forecast model using household income and number of typical appliances only. Establishment of trends in energy consumption. Also, determination of environmental impact of wind turbines on the following: wildlife, that is birds and bats, noise levels, land use, reduction in deforestation. Lastly, we also want to have research articles on technical and environmental aspects being produced. I thank you.
Thank you, Mr. Samira, and thank you, Lynn, for sharing the presentations. Colleagues, to those who have joined now, what we've shared is that the questions you can ask them on the chat box, and Linda will take note of the questions. And then we will still have a Q&A session after the last presentation. Then you can also still keep those questions, and we can engage on that session. So now, in the interest of time, I'll be presenting the last presentation in terms of my background, okay, I'll be presenting on system integration studies. My name is Basetsana Molefiani, as most might know by now. I'm a electrical engineer. Sorry, Linda, your mic is on.
Oh, apologies for that.
Okay. I'm a candidate electrical engineer at the Department of Public Works and Infrastructure, but I'm currently seconded with the CSIR Energy Centre under the Energy Systems Research Group. I started my career as a graduate engineer with Schneider Electric, South Africa, where I was responsible for the design and implementation of substations as well as mobile substations. And then I became a candidate electrical engineer with Public Works, where I'm responsible for electrical design and maintenance of departmental buildings. And then right now, I'm under secondment with the CSIR, and I'm currently, I'm seconded in pursuit of my professional registration with the Engineering Council of South Africa, and I'm responsible for assisting municipalities in assessing the impact of renewable energy sources to the distribution grid, and as well as microgrid modeling. I have a BSc Honours in Electrical Engineering obtained at the University of the Witwatersrand. So colleagues, in this session, I'll be presenting on system integration studies that were performed for the integration of wind energy to the Upper Blinkwater microgrid. So the contents of this presentation are as follows. I'll go through the background of this particular work activity, and then I'll give an overview on system integration studies that then looks at what are system integration studies and why are we required to perform them in order to integrate wind energy to the microgrid. Then I will present the grid integration studies that were performed for the UB microgrid. Then I will present what were the objectives to perform system integration studies, as well as the assumptions that were made, the methodology that was applied. Then I'll go through the power flow results and analysis of the results, give the conclusion of the results, and provide recommendations. So, in terms of the background for this work activity, as we've heard so far, the Upper Blinkwater project is a sub-project of the pilot project for the construction and sustainable operation of local energy grids based on renewable energies in the Eastern Cape. A microgrid system was designed to supply electrical power to the Upper Blinkwater village, which is a non-electrified village that is situated 23 kilometers from Port Bayport in Eastern Cape. So this existing microgrid designed to electrify the network is made out of a solar system, a battery bank for storage, and diesel generator. As CSIR, the implementing agent for integration of wind energy, we had to perform integration studies to safely integrate wind energy. So these system integration studies are performed in order to assess the impact of integrating 6 of 3.5 kilowatt wind turbine generators. So in this session, I'll be looking at what are system integration studies then. The purpose of conducting system integration studies is to conduct power flow analysis for the system integration, focusing on security of supply for electricity provision to the village, contingency analysis to mitigate any risk, and safe operation of the microgrid. So I'm going to unpack these 3 points in the next coming slides. What do we mean by security of supply? Security of supply is to ensure power supply to the village is secure and it balances with demand. So we are looking at system grid reliability. That means the grid should be reliable to supply power to the different homes. We are also assessing network integrity, meaning the network should be capable and adequate to carry power to the home. So the network equipment should be able to carry the capacity to the different homes. Balance between power generation and village demand. That is checking if this generation is adequate to supply the demand required by the village. When we're looking at contingency analysis, it looks at risk and these identified risks are mitigated. So this involves testing the integrated system under different conditions, under adverse conditions, minimum, maximum loading, okay, such as night conditions, prolonged cloud cover, etc. These are just examples. And then mitigating any risk, so analyzing potential system faults, and then making sure that the network is still redundant enough that even during the system faults, the grid is still able to operate. Then for safe operation of the microgrid, we need to verify safe operation of the microgrid to prevent any equipment being damaged due to mal-operation. So we are observing the thermal overloads of cables and transformers, and we're making sure that system equipment is sized accurately and is operated properly to avoid any damage to the equipment. Then we are also looking at insulation failure. That is now making sure that the system operating voltages are well within international prescribed limits to protect equipment and system from any damages. So this session, I'll be presenting the grid integration studies that were performed for the UB mini grid. So in order to perform these studies, we needed to define the exact objectives. So the objectives were to conduct power flow, which is load flow studies on power affected Dix Island, in order to assess what are the impacts that can occur when integrating 6 of 3.5 kilowatt crystal wind turbine generators to the microgrid, to the already existing microgrid, which is made out of a 75 kilowatt peak photovoltaic system, 2 of 65 kilowatt hour lithium ion battery bank, 1 of a 55 kVA backup diesel generator. And then the UB mini grid, which is a 400 volt distribution network for the UB, is then also modeled on Dix Island to perform these studies on the network, and it has a peak load of 54.4 kilowatts. These are the assumptions that needed to be made in order to model the grid on Dix Island. The first one, we had to look at load focus. So according to the implementing agent Lamisola for the existing microgrid, the peak demand of Upper Blinkwater was modeled at 55.2 kilowatt with a diversification factor of 80%. So as I've mentioned in the background, Upper Blinkwater was a non-electrified village, so therefore there was no information on load profile. However, Upper Blinkwater is part of the Greater Bishop Customer Load Center in the Eastern Cape, which includes East London, according to ESCOM demarcations. So Bishop demand profile was then taken with a peak load of 650 megawatt, and therefore modeled and therefore used to model the demand focus profile of the Upper Blinkwater. In terms of generation capacity, as mentioned, PV was modeled as a 75 kilowatt peak system with 80% performance ratio, and it had a 30 degrees tilt and a 0 degrees azimuth angle. In terms of wind resources, we model 6 3.5 kilowatt peak crystal wind turbine generators. And for the battery storage, we modeled 2 of Blue Nova 65 kilowatt lithium ion batteries. And for the generator, we modeled a 55 kVA Cummins S3.8 G6 cool pack diesel generator. So all this, we took the data sheet of all these equipment and modeled them on Dixieland. And then for the network, we modeled a 3-phase overhead line, sub-transmission line, which is a hair conductor. And for the overhead feeder cables to the household, a 4mm squared air deck cable was used. So here I'm just showing a screenshot of the model on Dixieland Power Factory. So just to explain what the different components are, here with the arrows, these are your load points, which are modeling the households. And then you would have from the bus bar, you would have a 4mm squared air deck cable, and also as a 3-phase overhead line, we modeled a hair conductor. So the data sheet of these cable were then modeled on Dixieland. Then you have a generation connection point, as given by the Lamusola in terms of the network. So here you would have all your generators, your PV, your battery, your wind turbine generator, as well as your diesel gen. So then, given that we have the model now, we then conducted system integration studies. To conduct system integration studies, we had to formulate scenarios. So scenarios are determined from studying demand profiles versus generation profiles of the area. The profiles are then used to identify possible worst-case conditions that could occur during operation of the microgrid. So, at minimum, high demand, low RE generation, and high demand, high RE generation, low demand, high RE generation, as well as low demand, low RE generation are the minimum worst-case scenarios. However, these scenarios we can then develop sub scenarios within these scenarios, which will make sense with the coming slides. Then we verify under these worst case scenarios, we verify thermal and voltage limits and ensure that they are within statutory requirements. So for thermal limits, we've observed at 100% of normal continuous rating for all conductors. In this case, as presented from the previous screenshot, there are no transformers on the network. However, there are line cables. Voltage limits are observed as statutory limit of plus minus 10% from nominal. As I've mentioned, you do have your minimum worst case scenario being your high demand. However, high demand is for illustration and high RE gen. However, you can have sub-scenarios within that where you identify if a battery is charging or if a battery is fully charged. So for just an example and overview, but I'll go deeper into it with the next coming slide. If you have high demand and high RE generation and a full battery, in such instances, it might happen that you will have an excess energy because if the RE generation is greater than the demand and the battery is already full, fully charged, therefore that excess energy cannot charge the battery. Then you would have wasted energy. But anyways, let me unpack it. On the results and analysis, the first scenario, minimum scenario I'm going to look at is high demand and low RE generation. So this occurs, the first profile you would have, I'm representing the demand profile. And then you would have a typical winter PV gen daily profile and a typical winter wind gen daily profile. So when we look at the profiles above, we can derive two possible worst case scenarios. So at 7 o'clock, you will have high demand. But then when you look at PV generation, at 7 o'clock, you have zero generation, 0 kilowatts. And again, as well as for the wind generator, there's no generation that is produced. So in this case, we've derived a sub-scenario saying high demand, no RE generation. And then we also have another sub-scenario, which is high demand, low RE generation, which I will illustrate in the next slides. So the first one, the one that I've mentioned, where you have no RE generation. In this case, we have 54.4 kilowatts as a demand, but total RE generation is at 0. So this results in a deficit of 54.4 kilowatts. However, you do have a diesel generator, and in the event that the battery is not is depleted, the diesel generator can only supply 48 kilowatts of power, of continuous power. So that means there is a deficit of 6.4 kilowatts. That in that instance, we have a risk of load shedding. The voltage profile was then also observed within the scenario where the diesel generator is assisting the RE resources. So in this case, we're observing it with the upper limit of 1.1 and lower limit of 0.9. So this is for voltages that are less than 500 volts. So when we look at the voltage profile, we do realize that it does decline, but nearly to a 0.98 per unit, which is well within statutory requirements. So the only thing that we notice is that there is a risk of load shedding in such instances. Now, when we go to higher demand, low RE generation, now this is with the support of the battery. So on a typical day where total RE generation is 34.8 kilowatts, PV given at 34.2 and wind at 0.6, and then we have demand at 42.17 kilowatts. That now gives a total deficit of 7.408, which the battery can then assist on supplying. So the voltage profile under the scenario, again, is still within statutory requirements. It only declines to about 0.99 per unit. Another minimum scenario that we considered was high demand, high RE generation. So looking at the profiles above, we could look at around 11 o'clock where you would have a typically high demand during high RE generation. These, just to mention, this is mainly to look at days, a single day at a time. So when you would have high demand, a typical day that you would occur where you would have high demand and high RE generation, and again on PV profile, it shows again at around 11 there's a high generation, and also on the wind generators it does show that it would have a high generation. So two sub-scenarios were then considered where you would have a fully charged battery, or you would have a battery that is charging. So for the case of a demand of 53.59 kilowatts and a total RE generation of 82.163 kilowatts, which again can be seen at around 11 o'clock from the above figure, this results in a surplus energy generation of 28.57 kilowatts. So if the battery is fully charged under this scenario, this surplus energy will then be wasted energy. Again, we then also looked at voltage profile in this scenario. It does show a decline, but it's about 0.98, which is well within the statutory limits. However, now in this case, another scenario would say that, okay, the battery is fully depleted, so that surplus energy is then maintained, and then it's charging the battery. So this would take the battery approximately 4 to 5 hours to fully charge the battery, provided that it's fully depleted. Again, this does show that the voltage profile is still well within limits under this conditions. Another condition would be low demand, high RE generation. And in this case, again, two scenarios are considered: low demand, high RE generation with a fully charged battery, and low demand with a high RE generation with a charging battery. So, as I've mentioned, the scenario happening at around 11, this shows a dip in demand at 25.07 kilowatts and a total RE generation of 56.64. And that now gives a surplus of 31.57 kilowatts. And that is excess energy which cannot be used by the battery or even the village. So that now results in dumped energy of 31.5 kilowatts that will be deemed as wasted energy and cannot be consumed by the battery charging. But however, the voltage profile was well within limits. And then with the battery charging, as similar to the previous one, that surplus energy can then be used to charge the battery, and it can take up to 4 hours to fully charge the battery. Now, within those scenarios, another thing that was looked at was thermal loading, which we saw that no thermal overloads were observed under all scenarios studied above, and all line loading were observed to be well within prescribed maximum loading limits. However, when it comes to contingency analysis, we did realize that the current network architecture for the Upper Blinkwater microgrid is arranged in a radial feeder configuration. This is the diagram shows below. And radial feeders are normally not good for redundancy and reliability, as when one section is undergoing maintenance, all the loads on downstream will be out of supply instead of one of the subsection of the feeder feeding the loads. So that is one thing that was observed. However, no thermal overloading was observed. So in conclusion, no voltage and thermal violations identified under studied adverse conditions. However, study did indicate that there is a possibility of load shedding and energy dumping, wasted energy. And then we did notice that for the UB 400 volt distribution network, that it's a radial feeder, which is not good for the redundancy and reliability. So to address those, we derived the following recommendation. The first one is that an operating philosophy to schedule and dispatch battery storage and diesel generation needs to be devised. This will then be fully unpacked by my colleague Fiona Olo tomorrow. So from the results, as I've mentioned, it is observed that there is a potential for the occurrence of load shedding and energy dump. So a coordinated method can be devised that will enable dispatching of battery storage and diesel generation, such that the system is more efficient in a way that it utilizes its energy sources. And then for the second one, it was recommended, it is a recommendation, that the UB's current radial feeder should be modified into a ring network architecture. So the current radial feeder of the UB microgrid network is to be modified in a ring network architecture that will allow for ease of maintenance and hence improve reliability of the network as a whole. So that is it from my side. I think now we can move on to the question and answer session. Lindo. Oh, John has a question. Lindo, are there any, sorry, John, I will take your question in a few, but just to ask, Lindo, are there any questions on the chat that came?
Thanks, Basi. No, I haven't seen any questions so far with regards to the presentations on the chat room. So you can go ahead and give John an opportunity. And also, I hope to the audience that you have been noting down, at least on a piece of paper, any questions that you may have had for the previous presentations that have been delivered thus far. Thank you.
Thank you, Lindo. John, you have a question? Maybe you can also specify which presenter you have a question for.
Right. Hi, it's John McIlvray here. I was the owner's engineer for the mini-grid. I'm from Africa Coast Energy. Just want to say thanks to the CSIR on the presentations. It's great to see the work that you've done. And I think it should benefit the mini-grid quite substantially. The first question that I had was actually on the recommendations that have been given on the Digslin models and studies. There are two recommendations, but I'd just like to know if the CSR took into consideration the layout of the community when putting together recommendations. Especially the second recommendation where it asks for a ring network to be done. If you look at the configuration of the communities basically stay along an access road, so it is it does not lend itself to a circular network, which obviously would be a better way of doing things, to have a ring network. And then the second question also comes in when you're talking about potential load shedding and dumping of loads. Was the CSIR aware of the operating protocols and procedures with the 4-stage load shedding that has been planned for the mini-grid in order to maintain the battery life and to ensure the LCOE and minimum use of diesel backup in order to make the mini-grid financially viable? Thanks.
Thank you, John. I think I can respond to that first, and then I think if Mbedi and Fiona want to also chip in, they can. For the first for the first question rather, which is the recommendation on the ring network, we then eventually did go on site and did realize that the distance is quite long to have a ring network, and that might mean more cost. So, however, this was just a recommendation in terms of when we are addressing an issue such as an issue that has occurred in terms of having a radial network. A ring network would be more beneficial. However, in terms of if we do more studies and more analysis, if the costs and implementation do outweigh the benefits, then the final recommendation would be to use the current architecture. And then in terms of the second one, we did notice that from the report we had, it did have a load shedding schedule, but it wasn't too detailed. So we then developed now an optimization strategy, which Fiona Lowe is going to present tomorrow, to then have a more to address the issue that we did notice that it did not have on the report from the Lamusola. It did not show the details, as well as ensuring that there's an efficient dispatching of the resources. So that is the reason why we took on a further analysis to developing a dispatch strategy to address that issue. I don't know if Mbedi would like to, or Fiona would like to come in.
Yeah. Well, okay. No, thanks a lot, Basitsana, and thanks, John, for that question. It's Mbedi here. Yeah, I think Basitsana has answered quite well, in terms of what the objectives were. But I think maybe most importantly is to realize the objectives around conducting load flow studies. The load flow studies recommendations were a due diligence in terms of assessing those load flow objectives, mainly, which is, I think Basitsana has highlighted, is network redundancy, its adverse conditions that may, obviously affect the network, such as cloud covers, problems of mismatch between load and demand. Obviously, considering the fact that you don't have dispatchability with your renewable energy sources, so that's the the shortfall that normally comes with this type of generation. Our conventional generation normally follows your load, so you don't have a problem of dispatching. You dispatch according to the amount of obviously fuel that you would feed into that type of generation, and you can easily follow the load. But with renewable generation, you are not able to do that, because you have to depend on the natural resource, which necessarily doesn't have to, which necessarily doesn't follow your demand. You can have a lot of generation in periods where your load is low, and obviously that would be a problem, and so on and so forth. So that was the aim of the load shedding. That was the aim of the load flow type of studies. Is just to do that due diligence. So those two recommendations that are emanating from that study then would put us in a good place to start investigating those recommendations further. For instance, in the first recommendation of optimization, of those resources, and we then did a HOMA study to basically see how we can be more efficient, with the way the power is being used, or the energy is being used in the mini grid. And this is notwithstanding the fact that the microgrid controller, the Siemens microgrid controller that is integrated there, already had provision for things like load shedding, so that was already there. We are very much aware of it. But the big factor here is that we needed to optimize the dispatch of the generation, and we have been in contact with Siemens themselves to tell them of our, this particular initiative of optimizing the dispatch. And well, they have agreed to actually implement the algorithm that we came up with into the microgrid controller to make sure that the energy is dispatched properly. Obviously, in recognizing that we have to ensure longevity in terms of battery life, that is as well has been taken care of in that optimization strategy that we have developed. So Siemens is very much aware, and we know the nitty-gritties of the controller, and we are just making things more efficient, and we are enhancing that particular microgrid controller so that the energy is better utilized. And yeah, so that is the situation in terms of the network development. We appreciate the fact that obviously, when the network was planned in terms of the network being radial, that there will be problems of obviously having a ring fit because of the landscape, of costs. Obviously you're working. I mean the UB crit mini crit was planned around certain constraints in terms of budgeting. So we are very much aware of that, but the study had to make that assessment. Remember, the load flow study normally just makes assessments in terms of network integrity and reliability, and then it has to give out recommendations. So that as well now would need a testing. It's just that we don't obviously have the mandate and the budget to go over and beyond what we have done in the load flow, which obviously, is that network development plan in terms of putting in a ring fit in the area. But as Pastor has said, that is just a recommendation, and you'll then need a proper network development plan that addresses cost-benefit analysis to see whether that will be feasible or whether what we have now is better, you know. So the load flow, those recommendations are due diligence for the load flow study, and we are going ahead with the first recommendation, and we have closed the loop in that regard in terms of making the system much more efficient. But in terms of the second recommendation, obviously we haven't. You need resources to undertake that type of a network development plan to see if it makes sense to actually provide a rain feed for the municipality. I mean, sorry, for the mini grid. Yeah. So I don't know if that addresses your question, John.
John, does that address your questions? I mean, yes, your question.
Yes, yeah, no, that's fine, thanks. I was just, yeah, I'm glad that they have had sight of the operation protocols, and if they do want to engage, or if CSR do want to engage with me at some stage on their findings versus how we've currently set up the mini grid, that would be fantastic. That at another stage, you'll see what happens in the presentation tomorrow. So thanks very much, and thanks for responding.
Yeah,
Okay.
we are very much aware of John. If you're in Africa Coast, we are very much aware of you. So we will be engaging when we have appointed them, because we are currently. I don't know if Andre is on the call, but we are currently in the process of appointing the EPC to actually integrate these wind turbines. We are very much aware of your role, and when the time comes, then we will engage you. Thank you.
Okay.
I think there are two questions.
Yes. Yeah. Thank you, John, for the question, and thank you, Mpere and Basitsana, for addressing that. So the other two questions are from K. Mbombela. Please excuse me if I mispronounce your name. And we have Alistair McMaster, who has his hand raised. So just to start off with Mr. K, his question is directed to Basitsana, and it is the question is as mentioned. He may have missed the point, but what happens to the waste energy? Is there a way or ways to store the energy for later use?
Okay. I think that's a good question. Because I think Mbeki even alluded to it in terms of renewable energy sources, that they're not load following. That means they depend on the resources in terms of either solar or wind. So in terms of the wind energy, the energy dump or the energy wasted. So like I've mentioned, there would be two scenarios. If the battery is fully charged, then that energy is then it is deemed or termed wasted energy. So that is why then we have to develop now an optimized dispatch strategy to minimize that wasted energy, or the occurrence of that wasted energy. So that energy is not stored anywhere. There are other implementation in terms of managing that, in terms of curtailing the systems. You can be investigated, but then that is why we then also investigated with the HOMA studies to see how can we minimize the occurrence of that. So I'm not sure if that answers your question, Kay Mbombela.
Yeah, maybe Mbombela just need to get it more clear that Basitsana has already said. Tomorrow, Fiona will be addressing exactly that in terms of seeing that energy is utilized properly. So there is a way of making sure that the battery is more optimal in terms of, yeah.
Yes.
Okay. Thank you, Basi and Betty, for that. It seems like Kay is satisfied with that response. And then I'll just hand over to Alistair McMaster to put forth his question. Thank you.
Morning. Can you hear me?
Loud and clear.
Thanks. This is Alistair McMaster from the Eastern Cape Provincial Government. In respect to these studies that have been undertaken, and the so I'm hearing that the CSIR have already approached Siemens with proposed changes to the algorithms for the grid controller. Have you consulted the owner's engineer for the grid around these proposed changes, and when are these proposed changes going to take place? Because I think we need to just bear in mind that we've got different components to the mini grid, which in the current configuration are assets under control of different entities. At the moment, the microgrid controller is under the control of the GIZ contract. So there obviously are sort of protocols and courtesies around how one would go about adjusting the system in the interests of integration. So I don't know, can you just indicate if that's to be taken into account around consultations for integration and also the sort of institutional integration that's tied to the technical integration and how one would consult the existing owner's engineer for that. So that's the one question. The other question I'd say is, has this modeling taken place based on, well, are these new algorithms based on modeled information or real-time information? So, we've got quite a number of months of data that are coming out of the grid controller. Has that been built into the information that's coming out here? Because I'd assume that one would want to provide algorithms based on the best possible information to ensure the integrity of the grid. So there's quite a lot of information that's come out of the controller already. Has that been built into the modeling so far? That's my other question. And then my third question is that we will be initiating a productive use of energy study in the next, well, we in the going into the procurement phase for that, where the excess power, the objective is to use the excess power as productively as possible through enterprise development in the community and so forth, or let's say just initiating some sort of productive use of excess power. So it'll be great to have information as to the sort of nature of the power that might be coming out, in terms of the quantity of it, the timing of it, and so forth, because then we can then try and match that to the best use of that power. So thanks very much.
All right. You are okay. I can go for it, Basta. Okay. Thanks a lot, Alistair, for those three questions. Okay. So I'll go in order. With the first one, in terms of speaking or approaching the owners engineers on the ground, we have to a certain extent approached over and above Siemens, who obviously are just the product developer. We have approached the EPC, which was on site, which is Lamosola. We've been working hand in hand with them. Our understanding was that AfriCoast was an owner's engineer for the integration of the PV system with the battery that was already there and the diesel generator. And we had to undertake, we were supporting UNDP in terms of looking for an owner's engineer again for now the integration of the wind. So we are instrumental in actually appointing AfriCoast again. I don't know now if I'm, if that has been final. Yeah, but we are very instrumental in appointing the the owner's engineer now and the EPC contractor for the wind integration. So that's why I said to John that I know that they have been handling the first portion or the first phase of the project as the owner's engineer. But on the second portion, we had to, again, I think we went through the tender process and we set the requirements for those owner's engineer. So when the time is right, we definitely are going to start engaging them in terms of our plans for the mini-grid going forward. So yeah, we are very much in the loop with UNDP, with Sanity. We are advising them, and the EPCs, Lamosola, Siemens are very much aware of what's happening. And like I've said, AfriCoast has just been integrated into the project again to look after the wind component as well. So we will be engaging them once everything is final with Kestrel turbines in terms of integrating of the wind turbines onto the grid. Andre will arrange a meeting where we will brief everybody concerned in terms of what our proposal is with the mini grid. So that's the first portion. In terms of the second portion of the question, of your set of questions, I think you said, Basitsana and Lindol, remind me here.
Yeah.
You basically, yeah, if you can remind me of the second part.
It's about the excess energy. It's to try and find out means of using it for a more other ways to using that excess energy. So he was just asking, what is the capacity? What values are we is that excess energy, and are we
Yeah, I remember
So,
it. I remember it.
Sorry, can I?
Yes, come again.
It was more just a comment around the excess energy. It would be great to interact and get the necessary information as one goes down the road around the enhancing the productive use of energy. So my second question was, to what extent has real data been used, like real-time data been used? To come up with those algorithms, or is this purely modeled information?
Yes. I remember that. Yeah. No. We obviously, like I said, I think Basitsana alluded to that when she started the presentation. The models are based on real data. The first challenge that we encountered obviously was there being not data for that particular village, simply because it was non-electrified. And to get typical data for a similar village also proved to be a bit difficult. So what we did there, we got the real data from Eskom, but of the larger municipal area there of the Bisho, and we scaled it down. We scaled it down to the village. So the village is in that customer load center. So the profile would pretty much be not very different from the larger Munich. So we just scale it down to depict that. So that profile is real. Real data that came, historical data that came from Eskom in terms of the larger Munich there, which is the Bisho. And so that came from there. In terms of generation and availability of resources of wind and of PV, that as well is real data that we got from Renewables Ninja in terms of modeling generators to for that particular resource level. So the resource level in the area has been derived from Renewables Ninja data that is obviously measuring the amount of the available resource in the area, and it's now that data was used to model the PV generation and the wind generation. So that wind generation is not just the profile of the generation is not coming. It's not a thumbs up. It's actually based on what's happening on the ground. So yeah, so there is that level of confidence in terms of trying to depict a reality to as much as we could. Yes, so that's the second question. And the third one, I think, was more of a comment, Alistair?
Yes, thanks. It was more a comment. But can I just, without wanting to interrupt the flow, I just wanted to clarify the question that I was asking. What I was saying was that there's the mini-grid control has been operating now for quite a number of months, and so there's actual real-time in operation data coming out of that mini-grid controller. And so I think where I'm coming from is perhaps taking a bit of a precautionary approach by saying one would probably be iterative in proposing updates to the algorithm of the controller by first taking the information of the performance of the controller and the whole system to date, and working that back into your models, and seeing whether that has any bearing on the algorithm, so that the algorithms are as responsive as possible to the latest information possible, so that we have the most optimal system. So I think my question is, have you taken the information and the data come out of the microgrid controller so far, which includes, for example, not transposing information from East London or elsewhere, but actually on site at the mini grid right now? Could you take that information and put it back into your models so that one can possibly fine tune the algorithms that are proposed to Siemens? Thanks very much.
Oh, okay. No, I hear you. No, thanks a lot for that question. Yeah, well, with the benefit of hindsight, it's always a better thing to do. But remember that when we undertook the study, just that now we are presenting the study now, but the study has been undertook, especially the optimization study, the dispatch optimization study was done like a year ago already. So when we undertook the study, we didn't have that benefit of, at that time, the microgrid controller had not even been integrated onto the mini grid. It was not yet there. So we had to do the study without that knowledge. But it's actually, I do understand you that obviously you could use that data to sort of like a fine tune. Yes, well and good. And if we had that later, we could have done that. It's just that we are at the final stage now where we are presenting to you. We are not necessarily still developing the model. It has been done like a long time ago. And obviously we even in terms of planning, is the normal standard procedure that is followed when you develop networks, and obviously in the absence of the real system not being there. So we just followed standard practices, because obviously non-electrified village would mean that you are not necessarily getting feedback in terms of how it's consuming. So if we have that benefit, like now, if it was now, then it would be very, very easy for us to go to the grid controller to tap in and see how the grid is performing, and to base our assumptions on what is happening on the ground. But there is absolutely no trace match in what we have done, I would say. Although obviously what you're saying would have been better if we had used what is currently what the performance that the mini grid is currently seeing. But saying that again, I just want to make it clear that sometimes you can go over a month, a year, even a year without getting into certain conditions that when you're modeling, you want to stress the network for. And it's very important that you stress those conditions, because sometimes they happen like once in like 5 years, once in 2 years, but when they happen, they're catastrophic. you know. So it doesn't mean that when you have a yes. So I was just saying that when you use real data, you need to be very careful that your modeling gets now, and if you only use the real data, your modeling gets very, very no, what is the word? It becomes limiting in a way, because it doesn't assume what could possibly happen sometimes.
Sorry,
you know.
Paddy, can I help you here?
Thomas, you can go ahead.
If I may, sorry to interrupt. Alistair, what may help, Paddy and Vasitsana are obviously talking from the perspective of looking at what is happening from the beginning. When I present tomorrow, I'll be talking about the costing model. And part of the development of this project included an ability to model what-if scenarios. And that allows you to go and play with various approaches, philosophies, demands, and so on. Paddy and the team did not have a demand profile for the mini-grid. Obviously, it's difficult. They did what seemed to make sense at the time to scale from a local region. Now, we may assume that in the absence of any other, that's not necessarily a poor profile to assume. But with the modeling tool, which I'll present tomorrow, you can now add for each household various different types of appliances, hours of demand when they come in and when they go out. Obviously, being an off-grid situation, you're not going to have thermal loads, you're not going to have geysers, which are going to respond in a different way. And you can now model the growth of the village, the growth of the electrical demand. You can increase or decrease your wind or PV supply. You can increase or decrease the amount of batteries, the capacity of the diesel generator, and your dispatch philosophy, whether it's strictly load following, whether it's assuming or trying to anticipate a load in the future to minimize the amount of diesel burn. So you get to do all your what-if scenarios with this particular tool and analyze the best approach. So that then allows you to anticipate what the consequences of certain approaches may be. Whereas if you take historical data, you are taking one specific incidence based on historical demand and historical supply. The modeling tool will allow you to tease out the impact of those individually.
Yeah, thanks a lot, Thomas, for that explanation. Yeah, I don't know. I think Thomas has explained it quite well, Alistair. But yeah, well, obviously there are different studies for that fit different purposes, and his will be obviously fitting that purpose of costing, and you will see it when he undertakes the study tomorrow. But yeah, I don't know if you still have a question, but yeah, well, we do appreciate your input in terms of modeling modeling using real time data. But yeah. So given the constraints that we had, we did what we could. I don't know if maybe that satisfies you.
Apologies just to interject there, but in the interest of time, it seems like we have run out of time for the allocated time that has been set out for this short course and presentation. But of course, I can appreciate that we started a little bit late due to technical issues at the beginning, and also there are other issues and questions that some people may want to address or ask. So I'm just going to ask the Ms. Program Director if you're going to allow maybe an additional 10 to 15 minutes to address other questions and concerns from other participants in this meeting, and if that's also okay with everyone else that's still left on this meeting. Of course, if there is a very urgent need for you to drop out, you're more than welcome to do so.
Yes, thank you, Lindo. As Lindo said, I think we would allow at least two or three more questions. I see Shambira, Mr. Shambira has his hand up.
Okay, before we address that one, there's one that was added onto the comment, and also I'd like to ask that from here onwards, just to keep your responses as brief as possible in the interest of time. So here we have on the comment sections, Atanda Raji, I hope I'm pronouncing that correctly. Have you conducted any social economic impact or benefit studies of the mini grid? If yes, can you discuss this? Mr. Shambira addressed this, saying that it will be, they stated, considered, and it will be discussed. But I'd just like to know if there are any other further comments to that question, or if it's okay, if we let it rest and it be addressed tomorrow.
I think for the interest of time, it can be addressed tomorrow, because I think Ms. Lisala will be presenting on that. So let's give other questions.
Okay.
Yeah.
Okay, then I'll hand over to Mr. Shambira for his question.
Two more questions.
Okay.
If you want to leave the course, you are more than welcome to leave if you have other engagements. But yeah.
Oh, okay, thank you very much. I just wanted to find out from Mr. Belly or Basesana about the load profiles, especially in terms of wind. Are we able, from the system when it is integrated now, are we able to measure load profiles specifically for wind, the wind component only, or it will only be getting load profiles for the whole system as a whole? Thank you.
According to my, as the system now, you are able to get profiles for most of the system components and equipment. Yeah, so I don't know if that's, you're asking if right now you could get access to real-time data, or
I mean measured data. Yes, but not now. We know that we can only access the solar part. But I'm talking about your integration of the wind component, the way that you are going to integrate the wind component. Are we going to be able to measure, to have the actual data or load profiles for wind component, wind energy only, or it is going to be combined from the end user?
We will be able, if I can assist Pastor quickly, we will be able to get that profiles for wind generation and for all generation that is there, including the load separately. So you can get like a profile for the wind separately from the PV, from the load itself. Yeah, so yeah, it's possible.
Okay, thank you very much.
I'm not sure. Thomas, do you have a question or?
Oh, sorry. No, I was just wanted to, Mr. Shambira, to make sure that I understood his question. Whether he was, I don't know if it was Mr. Shambira that asked the question, whether he was asking from a supply perspective, the supply from the wind turbine, or the demand, the load demand from the load, because he was talking about load profiles. But I think from the context, he means supply.
Yes, supply.
Yes, supply.
No, 100%. That'll also be covered to a degree tomorrow on the modeling, so you'll be able to tease out the different impacts. I understand you'd like to know what is technically measured, but you will also be able to see what we can anticipate from this particular region, this particular resource, using a typical meteorological year.
Okay. All right. Okay.
Okay, I think at 12:10 we can wrap up. Lindo, I don't know. Do you see any other questions coming up, or can we start closing?
No, I can't identify any questions or hands at the moment, so I think it's okay to wrap up now. Thank you.
Okay.